So a couple quick things. First of all, I'm just curious, how many people had a chance to go to BSpace and have a look at the slides for today's lecture? Or print them out? Okay, I see a few hands. So in general, what you can do is go to BSpace. I'll be posting the lectures, the slides for each week's set of lectures the week before. So this weekend, Saturday or Sunday, you'll see those up on BSpace. And you can print them out if you want to or not. It's up to you. But you'll see in the slides what material we're covering from the book and the subjects of each lecture if you want to have a look at that ahead of time. I've been getting a few emails from folks with questions. In general, I don't respond to emailed questions just for logistical reasons. With 650 plus students, it's very hard to do that in a fair way. So what I would like to do is, if you have a question from class, the very first thing to do is read the book. So a number of the questions I got were things that were right in the material in the book. So please have a look at the book, read the book material first. If you are still confused, then please come to office hours. You can come to my office hours. You can go to your GSI office hours, or you can go to Mike Meehan's office hours, or you can go to all of our office hours if you want to. Okay, so there's many ways for you to get help. We definitely want to answer your questions. We just want to be able to do it in a way that is fair to everyone. Okay. So today we're going to talk about the material in chapter 5 of your book, which is about the biological polymers. And basically, we're going to talk about the 4 different building blocks of the cell. These include carbohydrates, fats and lipids, proteins, and nucleic acids. And what you're going to see is that in all cases, these very big molecules, we tend to call these macromolecules because they're very big molecules, are made up of smaller individual building blocks. And so what I would like you to know, students always ask, do I have to memorize all of the the molecular structures, all of the building blocks? And the answer is, for Bio 1A, we don't ask you to memorize that, but you do have to know some of the important properties of these molecules and their components. So, and as we go through the material in lecture, I will point out to you what I would like you to know. Okay, so with that said, so as we said, all living things are made up of 4 classes of large biological molecules. Of course, there's lots of other kinds of molecules in the cell too, right? Water we talked about last time, lots of different kinds of small molecules, salts and things like that. But these 4 classes are the really big macromolecules that are important. And these molecules are all comprised of smaller units that are joined together to form large molecules. So in the case of carbohydrates, polysaccharides, these are made up of individual sugars that are hooked together to form polysaccharides. In the case of lipids, which are important for membrane structures in cells, these are made up of fatty acids. Proteins are made up of amino acids, and nucleic acids, like DNA and RNA molecules, are made up of nucleotides. And so what we'll do today is we'll go through each of these different classes and talk a little bit about some of the properties of these molecules that arise from the way they're put together and the kinds of things that they're going to do in the cell. And of course, we'll be talking a lot more in future lectures about how these molecules actually work. But today, we really just want to get the vocabulary down and really understand the basic properties of these kinds of molecules in the cell. Now, I have a little animation, and it wasn't working for me earlier, but let's see if it will work for us here. And it doesn't look like it's working. Okay, so in case that happened, what I did was I actually drew a very low-tech drawing here on the board, because I want you to understand that, and your book talks about this, that these polymers that we're talking about, so those include carbohydrates, proteins, and nucleic acids, DNA and RNA. These are all polymers. That means that they are long molecules that are made from a bunch of building blocks that are connected chemically. And what you should know is that in all 3 of those cases, these are molecules that are made by dehydration reactions. And so you probably remember from general chemistry that a dehydration reaction just involves the loss of a water molecule. And so this is sort of a very generic, simplified drawing showing you a growing chain of a polymer. And this could be a protein, it could be a piece of DNA or RNA, or it could be a carbohydrate. And in each case, there are enzymes in the cell that are able to catalyze the synthesis of these molecules by dehydration reactions. So we have the loss of a water molecule that leads to the linking together of an individual component onto the growing chain of this polymer right here to make a polymer that is 1 unit longer. And so the details of course, the enzymes that do this are different in each case. The component building blocks are different. But if you look at the underlying chemistry, it's actually the same. And an important thing to also know, and your book has a nice figure showing this, is that the opposite of dehydration is of these dehydration reactions is hydrolysis. And so when these molecules are broken down in the cell, you actually have water being added across one of these bonds to release an individual unit. And there are enzymes in the cell that are capable of catalyzing hydrolysis reactions. So when the cell has to recycle a protein or recycle a molecule of a carbohydrate or break it down for energy, this is the type of reaction that will be going on. Okay, either dehydration when you're synthesizing one of these polymers, or a hydrolysis reaction when it's being broken down. All right, so with that, let's start talking about these individual molecules. So carbohydrates, you probably know, are very important as fuel, right, in our diet, for example. And it turns out that carbohydrates are used all across biology also as structural molecules. They're incredibly important for building cell structure and for the properties that we observe in various kinds of organisms. So it's important to know a little bit, at least, about how these are put together. So they are carbohydrates basically include sugars and as well as polymers of these sugars. The simplest carbohydrates are called monosaccharides. These are simple sugars, molecules like glucose. You've probably heard of fructose, right? These are simple sugars that form the building blocks for much larger carbohydrate molecules when they get linked together. And carbohydrates that are macromolecules are called polysaccharides. And so again, these are polymers that are composed of different types of sugars. And by the way, there's many different kinds of carbohydrates depending on the type of sugar that's used to make the polymer. But we're going to focus on a few specific kinds of carbohydrates here because they play really, really fundamental central roles in biology. Okay, so a little bit about monosaccharides. If you ever see a chemical formula that has this sort of basic multiple, you can be pretty sure that it's probably a monosaccharide, okay, CH2O. So multiples of that chemical formula tell you that this is probably some kind of carbohydrate molecule. The most, I don't know if it's the most common, it says here the most common, certainly one of the very most common monosaccharides in biology is glucose, and it has this chemical formula, so you can see that's a multiple of this basic unit here. And the way these are classified is by the location of a carbonyl group, and these can either be aldoses or they can be ketoses, depending on where the carbonyl is located. And if you look in your book, they have a very nice discussion of the different ways that we can represent the chemical structure of sugar molecules. And again, you may remember this from general chemistry class, that these molecules can be drawn as linear molecules. They can also be drawn really more accurately as circularized molecules, which is the structure that they form when they're in aqueous solution, such as in the cell. Okay, and so the number of carbons in the carbon skeleton defines the type of monosaccharide that these are. And so, as we said, these serve as major fuel for cells, and they're also the raw material for building much larger molecules that play important structural roles in the cell. So this diagram here, again, this is taken from your textbook. This shows an example of this kind of reaction here, in which 2 individual monosaccharides, a glucose molecule and a fructose molecule, are being linked together to form a disaccharide over here, sucrose. Everybody know what is sucrose? Table sugar, right? Yeah. okay? Sucrose over here. And a couple things that I want you to be aware of. This bond between the individual monosaccharide units is called a glycosidic bond, a glycosidic linkage. And this linkage can be formed in different ways depending on the orientation of the hydroxyl group that is being linked together. It's connecting the two monosaccharides. So this is a 1,2 glycosidic linkage. We're linking together the number 1 carbon and the number 2 carbon on this sugar over here to form this glycosidic linkage. And again, there's many different ways. If you look in the book, they show you some different examples of disaccharides and larger polysaccharides that have different kinds of glycosidic linkages. But in every case, the linkage looks like this. It just might have a different orientation with respect to the sugar ring. Okay. And again, this is showing you an example of a dehydration reaction used in the synthesis of this type of molecule. So it's an example of a condensation reaction losing water. And as I said before, the reverse reaction in which water is added across the bond is called hydrolysis. And so in the cell, there are enzymes that will catalyze both the synthesis and the breakdown of these kinds of molecules. Now, these molecules can get really, really big. Okay, so there are lots of interesting structures in the cell that are formed from very, very large carbohydrates that have up to thousands of individual monosaccharides that are all chemically linked together to form these kinds of polysaccharide structures. So this is showing you two examples that are very common in biology that I want you to know about. One is called starch. Two examples of this are amylose and amylopectin. And so these are polymers of glucose in which there are 1,4 linkages, 1,4 glycosidic linkages between individual glucose units that are hooked together to form these very large carbohydrate molecules. And you can see that in the case of amylopectin, these molecules are also branched. And so each of those branch points is a 1,6 glycosidic linkage, okay, between the carbon number 1 of one sugar unit and the carbon number 6 of an adjacent one to form that branch point. These are large carbohydrates that are found in plants. So this is how plants tend to store energy, is they will take individual glucose molecules and use enzymes to hook them together into these large starch molecules that are then storage units for energy. When the individual glucose molecules are needed for metabolism, they can then be released by clipping them off this large structure. Over here is an analogous kind of structure that's found in animal cells, our cells, for example, called glycogen. And this is a structure that is similar to what we see over here for starch in plants, except that there's a lot more branching that goes on in these structures. But these are, again, 1,4 linkages of the individual glucose molecules that make up these large polysaccharides. What's another very large polysaccharide that's incredibly important in biology? Does anybody know? Cellulose, yeah, cellulose, right? So cellulose is a polymer that is very, used in plants, of course, to make things like tree bark and make the structure of a leaf and other sorts of plant structures that are very rigid. The thing about cellulose, and I urge you to read your book about this because they have a very nice discussion. And this is a sort of a really interesting thing in biology. It turns out that chemically, cellulose is actually not that different from glycogen, except that there's a very important structural difference in the way that the adjacent glucose units are hooked together. They're effectively hooked together such that in the cellulose molecule it forms a structure that's incredibly difficult for enzymes to get access to. So, for example, our cells we actually can't digest cellulose, right? If you try to eat tree bark, you don't get very much nutrition from that. And the reason is that we actually don't have the ability to digest cellulose, and many organisms don't. Organisms that have to survive on cellulose often have microbes, bacteria, that are specially evolved to be able to digest cellulose with special enzymes. And this is one of the reasons when you read in the media about biofuels and people wanting to use cellulose, make cellulosic ethanol, for example, one of the reasons it's really challenging to do it is that it's difficult to do enzymatically. Chemically, it's actually not that easy to break down cellulose. All right. Okay, so let's move on to lipids. So these are a diverse group of what are called hydrophobic molecules. So the word hydrophobic means afraid of water, right? Afraid of water. So these tend to be a class of molecules that don't dissolve in water. They don't form good hydrogen bonding interactions with water. They are actually not real polymers. As you'll see, they're formed from smaller individual building blocks, but they actually are not polymers in the same sense as we see for nucleic acids or proteins or carbohydrates. And the unifying feature is they don't interact well with water. They don't form hydrogen bonding interactions with water. They don't dissolve in water. And this is largely because they consist of mostly hydrocarbons. So these are compounds that have mostly carbon and hydrogen components, right? So these actually, the kinds of bonds between those atoms tend to be nonpolar covalent bonds. So they actually don't form the kinds of polar covalent bonds that we talked about last time with water that make them amenable to the kind of hydrogen bonding interactions that form when you have interactions with water and other molecules that form polar covalent bonds. The most significant of types of lipid molecules in biology are called fats, phospholipids, and steroids. And so we're going to look at each of these types of lipids. So what makes lipids not true polymers? Stay tuned because we're coming to that. Okay? So fats are constructed from two kinds of smaller molecules, a glycerol molecule, which is a type of sugar that has 3 carbons in the backbone. Okay? 3 carbons in the backbone, not 6 like we see in glucose. And fatty acids. Okay? So glycerol has 3 carbons. It's an alcohol with a hydroxyl group attached to each carbon. And a fatty acid consists of a carboxyl group attached to a long carbon skeleton. And the next slide shows how these actually come together to form a molecule of fat. So here's the glycerol molecule right here. There's the 3 carbons in the backbone. There's the oxygens. And these basically get esterified to each of them to a fatty acid molecule shown here. Now, in this example that they're showing you on this slide, so each of these bonds is a single bond, and so this fatty acid is called a saturated fatty acid. Okay, it's fully saturated. In other words, it has as many hydrogens as it could possibly have based on the bonding chemistry of carbon. So it's called a saturated fatty acid or saturated fat, and these kinds of fats are showing you a stick of butter there because these are fats that tend to be solid at room temperature, right? And the reason is that they tend to pack together, the chains in these fat molecules tend to pack together very tightly because they are fully saturated and they have a very regular kind of structure that allows those chains to pack together very tightly. So they tend to be solids at lower temperature, at room temperature. And that compares to what we see for what's shown down here, which is called an unsaturated fat molecule. And here, what you see is that, again, we have the same glycerol backbone, the 3-carbon backbone. We've got these esterified oxygens over here. But then what you see is that for this one fatty acid, it's actually not fully saturated. There's a double bond right here. And the consequence of that is that it has a bent structure, as they're showing you right here. And by the way, this is called a cis double bond, right? And what would a trans double bond look like? One's up, one's down, right? So yeah, trans. So if we had a trans double bond, then these, again, you sort of have a kink in the chain, but it tends to look a little bit more like this molecule right here. And so a lot of baking companies a while ago, decided that they would start saturating artificially plant fats, which tend to be unsaturated. So olive oil, things like that, tend to be unsaturated, have unsaturated fatty acids in their lipids. So those oils, those plant oils, tend to be liquid at room temperature, not solid like animal fats, like butter. But the problem is that when you artificially hydrogenate these molecules, oftentimes what happens is that these trans double bonds get introduced, and these are, so when you read on the label of a package of your favorite cookies or something, it says trans fats. That's what they're referring to. And so those trans fats have the property of making those fats tend to be solid at room temperature, so they can be more useful for cooking, and they tend to have a longer shelf life. The problem is that in our bodies they're not metabolized very well, okay? Because they're actually not, they don't really look like natural fats. And so what's been found over the years is that those kinds of fats actually tend to build up in our arteries, and they lead to problems like atherosclerosis, where you have fatty plaques that are building up in the arteries that lead to eventually to cardiovascular disease. So there's been a big push to try to get rid of trans fats, and you're probably aware of that. But this is the chemical basis for what that really means. Okay, so what about phospholipids? So it turns out that these are incredibly important in cells because they actually make up cell membranes. And the reason that they're great for making up cell membranes is based on their chemical structure. So these, again, have the same glycerol 3-carbon backbone, but in this case, they have two hydrophobic tails, two fatty acids that are hooked on. And then at the third carbon, instead of a fatty acid, we have a phosphate head group. And so as a consequence, the structure of this molecule has the interesting property where the fatty acid chains kind of hang down, and these are hydrophobic. They tend to be very hydrophobic, whereas this, what's called the phosphate head group, is hydrophilic. And so if we look at just a very schematic drawing of a phospholipid, it kind of looks like this. And so these molecules can pack together very nicely to form what's called a lipid bilayer. And again, there's some nice pictures in your book that show this, where the hydrophobic tails are all packed together in a line, and these hydrophilic phosphate head groups are all packed together. And so you have a very nice barrier. And the reason it's called a bilayer is that, of course, that doesn't work to just have one layer of those. You actually have to have a second layer where all the hydrophobic tails are pointing in towards each other, and the phosphate groups are lining the exterior, because, of course, the cell is an aqueous environment. So those head groups are hydrophobic. They want to get away from the water. They avoid water, and the water structure tends to form with hydrogen bonding interactions around these phosphate head groups. Okay, and then the third type of lipid I want to point out to you are a class of lipids called steroids. We've heard lots and lots about steroids in the media, right? Lots of athletes using steroids, et cetera. What are steroids? Well, it turns out these are all based on this kind of chemical structure that you see right here. It's a 4-ring structure. So if you ever see a molecule that has that kind of 4-ring structure, you can be pretty sure that it's probably some kind of a steroid. Now, these are really important molecules in the body because these are often the building blocks for hormones, right? So for the sex hormones, testosterone, estrogen, other kinds of related hormones are built on this kind of a backbone. And what you're seeing here is a molecule called cholesterol. I think we've all heard of cholesterol as well. And this is actually a very important component of animal cell membranes. We often we read in the media about cholesterol. We're often reading about the dangers of cholesterol, trying to make drugs that reduce cholesterol levels, that sort of thing. But it turns out that actually we need cholesterol, right? It's actually an essential component of membranes. And when we talk about cell structure next week, we'll talk more specifically about what cholesterol is actually doing in the membrane. But you can see that it has a lot of hydrophobic character to it. So these molecules can actually sit inside in the hydrophobic interior of the membrane, which is where they tend to hang out. And cholesterol is essential, but you also know that if we have too much of it, it can also lead to cardiovascular disease. And there's a lot of research that's gone on to try to understand the metabolism of cholesterol and what happens in the body. There's lots of macromolecules, proteins, et cetera, that have evolved in cells to handle cholesterol, bind to it, transport it different places. So very, very important to just understand the basic structure of this molecule. And like I said, next week, we'll look at what it's actually doing in cell membranes. Okay, so proteins. Proteins actually account for almost 50% of the dry mass of most cells. So these are incredibly abundant type of polymer in the cell. And what do proteins do? And your book has sort of a 2-page spread on this in chapter 5 with cartoons that illustrate all of this. But basically, these are found in cells that are incredibly useful for all sorts of functions, such as catalyzing reactions and other sorts of transport properties, structural properties of the cell, signaling, binding to cholesterol, all these sorts of things. Many of these functions are carried out by proteins. And what are proteins? They're basically polypeptides. And I want to just be clear about the nomenclature here. So you'll see the word protein. And when we talk about a protein, in general, we're talking about we're always talking about a polypeptide. Okay? In other words, a long polymer that's built up of individual amino acids. But we're typically talking about a protein. We're typically talking about an amino acid polymer that's longer than 100 amino acids. Typically, okay, it would be a protein. If it's smaller than that, then we might refer to it as a polypeptide. Okay, a polypeptide. And these are polymers that are built from a set of 20 common amino acids. There's a few other types of amino acids that are found in nature, but they're quite rare. Okay, and as we talked about last time, what's interesting in biology is that all proteins in all the organisms that we've ever studied have the same set of 20 amino acids. So all proteins in biology are built from the same set of 20. And that's why we can do experiments like replacing a yeast enzyme with a human enzyme that has a similar function. That experiment doesn't always work, but it often does. And the reason is that these proteins can be very similar in the way that they are made chemically and in the way the kinds of structures that they can form. Okay, that's because they're made of the same set of building blocks. And a protein molecule, as I said, sort of the nomenclature is set up such that we're typically talking about a